Hello everybody and welcome to chapter 8 in statics. My name is Professor Algarra and I'm going to be talking about friction. In this video I will introduce you to the topics, I will go in depth, and then we will have a few exercises. This chapter is not that short and it's not that easy. I mean, it's one of the toughest chapters. I would advise you to pay attention to everything that I will say throughout the presentation, but also go and read the book as many times as needed so you can get and absorb the knowledge. I will have a few exercises as always so you can see, how theory will look like with numbers. All right, so friction is defined as the force of resistance acting on a body which prevents or retards slipping of the body relative to a second body. So right now, you will have an object like the one you're looking at, and this object will have its weight, but let's say a force P is applied to it that will cause the object to move. Between this object and the surface, which will be object 2, something will happen, and that something is called friction. I'm pretty sure you've heard of this before in physics. So experiments show that frictional forces act tangent or parallel to the contacting surface in the direction opposing the relative motion or tendency for motion. So as you move to the right or the left, a force will be created in the opposite direction of the tendency for motion. So if you're moving to the right, then a force will be created to the left. So the surfaces, as you can see here, this is an object and then you have the surface. When you look into the inside, you will see imperfections that are happening between one body and the other. This is the surface and the object. These imperfections will cause a resistance to the movement, and the frictional force will be steady, throughout the movement, throughout the experiment until it starts to move. But I will get into that later. So for the body shown on the picture, this one to be in equilibrium, the force has to be equals to P, because force is equals to P and the normal force is equals to the weight. What it says, it's what we've been discussing from day one, which is sum of forces in the x direction will be equals to 0, sum of forces in the y direction will be equals to 0, and maybe also also the sum of moment at a point in the object will be equals to 0. So the three equations of equilibrium, they need to be satisfied in order for the object to be in equilibrium. This is pretty much, same thing that we've been talking from day one. So to study the characteristics of friction F, we need to assume that tipping does not occur, that this guy will not move in this direction, that tipping will not occur. Then we gradually increase the force, the magnitude of the force P. Typically, experiments show that the friction force varies with P, as shown on the picture above. So right here, as you so you have to look at this picture. As I said, you apply P, and that P will be at t equals 0 will be like this, but then maybe 3 seconds later will be like this, and then later will be like this. It will be increasing with the time. As you are increasing that P, motion will not happen until you reach its maximum. As you move, you will have more force, or more P, more P and more P until you reach its maximum, and then after that you will have motion. Okay, so what is very important here is for you to realize that at this object, at the beginning will not move, and as P it's being applied to that object, then it will need to how can I say this? So P will need to win over the frictional force for the movement to start. And that's all you have to picture in your head, and I keep saying this, especially when I'm teaching dynamics. Try to think of everything like at the beginning of the experiments and then at the end. T equals 0 and then T equals T. And this is not said on the books, but like I said, just try to picture that in your head so you can start realizing what is about to happen. So like I already said it in the previous slide, the maximum friction force is attained just before the block begins to move. Like I said, if I go back to the picture, P will be given, or P will be, how can I say, P will be applied to the object, and there will not be any movement until it wins over the frictional force. So let's just read what it says. So the maximum friction force is attained just before the block begins to move. The value of that force is found using the equation, frictional force, static frictional force will be equal to mu s and times n, where mu s is called the coefficient of static friction. The value of mu s will depend on the two in contact, and that is usually given for your level right now. Mu obviously can be determined with experiments, but that's not the object right now, okay? So once the block begins to move, the frictional force typically drops, obviously, and then that force will be calculated at F sub k. It's equals to mu k times the normal, where mu k is the coefficient of kinetic friction, okay? And Fk is the frictional force in motion. So as you start to move the object, then you will have a force that is resisting that movement, and that force is called kinetic frictional force. As far as static goes, we're studying only everything when it's not moving, and that's why your life right now is a lot easier before you get into dynamics, and that's when we will start to study the kinetic movement and so on and so forth. It is also very important to know that the friction force might be less than the maximum friction force. So just because the object is not moving, don't assume that the frictional force it's at its maximum, okay? Unless you're told or know that motion is impeding. So what you need to realize from all of this is this particular graph and the same example. You have your surface and then you have an object. As P is applied, you will start, the object will try to move, but you have an opposite frictional force that is resisting that movement. As you go, from the beginning to the end, P will be large enough to start winning over to the frictional force, and therefore we will have movement. As you look at this, which is the part that we're studying, at the beginning, when P is 0, as you start moving, your frictional force will try to fight against P, until it reaches its maximum. Up to this point, you have no motion. Right after that, then you have motion. What matters here is that you cannot assume that it will reach all the time at its maximum. You might have some cases, and I think in one of the exercises that we'll be solving today will be the case in which we need to calculate the maximum P so something can happen. So that something can happen could refer to this point maybe, or this point, or this point. What I'm trying to tell you is that you cannot assume that it reaches its maximum unless you've been told. Typical values for MS are given in the book. You can go and take a look at it. There is an experimental way to get mu, and that will depend on the materials and so many other things, but the table is given, it's on the book, and with that table you can solve the exercises for now. So how do we do the problems, and this chapter, unlike the other chapters, you have to think a little more. In the past I gave you like a recipe that could be followed, but right now you need to play with everything that you have to, so you can choose the shortest way of getting the answer or the easiest way to get the answer. But there is a procedure given by the book, so let's just go through it. So at first we need to draw the necessary free body diagrams, and we need to make sure that we show the frictional force in the right direction. Remember that we'll always oppose the motion, or tendency of motion. Then we need to obviously look at the free body diagram and determine the numbers of unknowns. We cannot assume, and again, we cannot assume that the frictional force will be calculated at its maximum, remember, unless you've been told or something like that. Then after that, we need to apply the equations of equilibrium to find those values. So what about impeding tipping versus slipping? When a force it's applied, let's say, and take a look at this example, when a force is applied at this point, it could slide, but it could also tip. How so? Well, at this point, you could have something like this. At first, you have this, but then later on, it could tip over, which will cause this object to go like this, tipping about this point, in which you will have the same box, but now like this. And as you do that, this part of the object will start departing from the floor or from the ground. Okay, that's what tipping is. So for a given W and H, obviously, width and height, how can we determine if the block will slide first or tip first? In this case, we have 4 unknowns, when that happens, and only 3 equations of equilibrium. So therefore, we need to make assumptions to give another equation, and once we solve the equations, we need to check if our assumption was correct. So, how so, you might ask, Professor, how do I do that? There is a right path to follow these assumptions, and then we can basically confirm these assumptions as I'm about to show you. There are 2 possible cases. You have slipping or tipping, okay? Usually, and that's just something that I do normally, but you can do it differently if you want to. You would assume that a slipping occurs. When a slipping occurs, you will assume that the force is at its maximum. Okay, the frictional force is at its maximum, and you have the equation, which is mu s times the normal. Okay, once that is attained, you need to look at the picture right here. Why is that? Because then we need to look at the position of the normal force. As you try to move this guy, the normal force will change, and you will have more normal into one point on the surface, and you need to locate where that would be. If that location of the normal force is between the center and half of the object, then your assumption was correct. Let's say, for example, that you get, after you assume that force is equals to mu s times the normal, and then after that you realize that your normal was actually located outside of the box, then your assumption was wrong, and therefore you have to go to the next assumption, which is when tipping occurs. Let me show you something. Let me just go back to this. Let's assume that you have tipping, and I'm trying to, to explain this in the best possible way. It might not be the best explanation, but at first you have this. Right here, if it's sliding, right, you have your normal force. And the normal force will be like this. Right? And this is given by the weight, obviously. As you can calculate a resultant force, and maybe your resultant force will be here, which is between the center and half of the object. Therefore, sliding is occurring. With tipping, it's a little different. Let's say at t equals 0, you have the object as you can see here in the picture. And then after the P is applied, you find out that your object is now like this. And we need to look very closely at right here, as the surface, as the surface in contact is no longer in contact, your only normal force will be applied only at the end, because now you know the location when tipping occurs. When this is about to tip, or when it's tipping, all the normal, it'll tip about this point right here. Therefore, that's the only point in contact with the surface. That's the only point in contact between the two bodies, and therefore your normal force will be located at the end. And that's the assumption you make for the next one. When tipping occurs, you know that the location of your normal force is right here, where x will be equals to b divided by 2. And then based on this assumption, you will calculate your frictional force. If that frictional force it's less than its maximum, tipping occurs. Okay, and if it's not, then it doesn't occur. So at first, like I said, wrapping up a little bit, when sliding occur, and take a look at this, because this slide right here is what you need to solve these exercises. When sliding occurs, and that's what you will be doing all the time, your maximum condition, when you're designing, you have to design based on maximum or critical conditions. Your critical condition will be that the frictional force is reaching its maximum. But for that to happen, the normal has to be between the center and the edge of the object, okay? If it's between 0 and b divided by 2, being b obviously it's, from one face to the other. If that's the case, then boom, slipping occurs. If it's not that, and you get that your frictional force is maybe outside, which is wrong, then you have to check for tipping. For tipping, you will assume, right, that your normal force, it's located right at the edge, which is x is equals to b divided by 2, which is b, this b, divided by 2. With that, you will solve the equations, and you have only to check that F will not be greater than the maximum force. If you check that and this checks out, then tipping occurs, you can move along, and your problem will be solved. There is a lot of, confusion with this, and I know that at first when you see it, it's not as clear as you might think, okay? And I will stop right now and tell you that if you need assistance, let's just schedule a Zoom meeting, and I will try to explain you this in a better way, one-on-one. It'll make sense. But I'm hopeful that with this exercise, it'll clear your doubts. So we have a crate that it's been under, force P, and then we need to calculate the maximum force P that can be applied without causing movement of the crate. Remember that we're still working we're still working in this area. No motion. Don't forget that. This is where we are right now. We don't care about the motion because this is not dynamics. What would be the solution for this? Well, we need to draw a free body diagram of the box. We can then make our assumptions. Then we need to use the equations. Then we need to check the assumptions, and that's it. That's all we need to do. So, when we look at this, it's very important that we get the free body diagram. We have P right here. We have the weight, which is giving. We have the frictional force, and we have the normal force. And we're locating normal force x distance from the center. Okay? There are four unknowns here. We have P, the force, then the normal force, and then x. Like I said before, we will assume that the crate slips. We're going to use this case right here. Slipping occurs. And therefore, I will assume that the maximum force will be equal to 0.4 newtons, mu sub s times the normal. Okay? So now I will have my first equation, so I can solve, my system of equation. What do I do now? Well, now that I have that, I will just do sum of forces in the x direction, and that will be equals to P minus 0.4 n, and it's equals to 0. And then sum of forces in the y direction will be equals to normal minus 250 will be equals to 0. That looks pretty simple because so with this, solving the equations, I will get that P it's equals to 100 pounds, and then the normal force will be equals to 250 pounds. Okay, so it seems like it's good. So now we need to find X so we can check our assumption. And if I go back to this, that's what we need to do, right? We assume this, we solve the equations, and then we will check that X it's between, that range. What do I have to do in order to find X? And this is where everything that we have learned will take place. So we just need to make sum of moments around this O. Okay, so if we do that, we'll say sum of moment around O. Don't forget your sign convention. That will be equals to 0. So therefore I have minus 100, that multiplies 4.5. That's the P I got, and then I have 250 that is been multiplied by X, this guy we just calculated, and that will be equals to 0. When I solve for X, I will realize that X it's equals to 1.8, which is right here outside of my range between 0 and 1.5. Because this one is more than 1.8, I will know that sleeping will not occur. And now that sleeping will not occur, I need to check for tipping. Okay? So like I said, we assume that the box would slip, but then we got our values, and then when we check, it was not the right one, it was outside. So all of the calculations that we did before are now, done, and we need to move to the next assumption. That would be for tipping. If I go back again for this, tipping occurs, this is what I will assume. I will assume the location of X, I will solve the equations, and I will just only check that the frictional force is not more than its maximum. So if I do that, this is my assumption. My normal force is right at the edge. If I do sum of forces in the X direction, sum of forces in the X direction will be equals to P minus F, and that's equals to 0. Then sum of forces in the Y direction, I will have the N minus 250, it's equals to 0. If I solve the system, I will know that the force, the frictional force, will be equals to P, and I will also know that the normal force it's equals to 250 pounds. Okay, so if I do now sum of moment around O, I will get that it's minus P that multiplies 4.5, which is the distance, and then I have plus 250, which is the normal, that is been multiplied by 1.5, which is the location, that's what I assume, and this is equal to 0. If I solve for P, I will know that P is equals to 83.3 pounds. So all we need to do now is to, check for the maximum force, and we know that the maximum frictional force will be equals to mu S times the normal force. So if I multiply 0.4 times 250, I will get that this is equals to 100 pounds. Therefore, I realize that P it's actually less than the frictional force, or the maximum frictional force that the crate can attain, because I will call F max, so there's no confusion between this and this. So I realize that P is not greater than F max, therefore my assumption was corrected. If I go back to this, that's what we did, right? We check, we place the location of the normal force, we solve the system of equations, and we check that force is not greater, my maximum force is not, the force that I get is not greater than the maximum force allowed. Therefore, my assumption was right. And then you can consider that the exercise is done. Okay? So now we're moving to another topic in the chapter, which is wedge, the analysis of a wedge. So a wedge is a simple machine in which small force P is used to lift a large weight W. To calculate the force required to push the wedge in or out, it is necessary to draw a free body diagram of the wedge and the object on top of it. It is easier to start with the free body diagram of the wedge, since you know the direction of the motion. You know, this is the wedge right here. You know that it's moving like this, so you might want to start with that. But you have to know that the frictional force are always in the direction opposite to the motion, okay? Or like we said, the possible motion. The friction force are along the contacting surfaces. It's always parallel to those surfaces. And then the normal forces are perpendicular to the contacting surfaces. That's all we need to know in order to treat these exercises. It's just another case in which frictional force will be considered. So, for example, if you have the wedge, let's say we want to do a free body diagram on this particular wedge. This would be this. We have the normal exerted by the weight, which is perpendicular to this surface. And then you have the frictional force that is going in the opposite direction of the movement, right? And then we have a frictional force that goes between this side and the surface in which this side is in contact with. And obviously there is a normal force perpendicular to that thing. Once you have that, you can then draw, after drawing the free body diagram, you have to calculate the unknowns by using the equations of equilibrium as we've been using from the beginning. So at the contacting surfaces between the wedge and the object, the forces are equal in magnitude and opposite direction. So if you have a force at the wedge, if you had a force going into this direction, it means that when you go to the weight, it'll be in the opposite direction, of the wedge. Okay, so once you have the two free body diagrams, you have to look at both of them and realize which one you're gonna do first with the equations of equilibrium, and that will depend purely in the case in which it's given. So if you have the two free body diagrams of the two objects, this is object A and this is object B, by looking at it and realizing which ones are unknowns and knowns, then you will apply equations of equilibrium, whether to this one first or the other one first. To be quite honest, when we're treating these exercises, usually you will look like right on very instantly that you only need maybe a sum of forces in one direction, so you can carry this value into the next one, and then you can solve all of the unknowns. That's usually the procedure that we follow as engineers. And let's just give an example, as always, And for that part of the chapter, I decided to go with like two different problems, so you can see variations of each one of them. But anyways, let's just read the statement. The 3,000 pounds load is applied to wedge B. The coefficient of static friction between A and C and B and D, it's 0.3, and between A and B is 0.4. Assume the wedges have negligible weight, so you don't have to worry about the weight. We need to calculate the smallest force P needed to lift this guy up. Okay, so the plan would be to draw the free body diagram on both of them, and then it says right here that we have to go with that, but I will stop you right now. We will draw the free body diagram, and then by looking at them we will make the decision whether to go with B first or A first. So we draw the equations of equilibrium, and this is A. We have P like this. As you try to move this one in, you will have a force, a frictional force that is going in the opposite direction, both of them. This one will be equals to 0.3 times the normal C, and this one is 0.4 times normal, okay? The normal of the other object. Then you have normal C, you have the normal coming from the object, okay, cool. On the other one, B, you have the force that is being applied to it. You have the normal force because of the wall in which it's resting, and then you have obviously the frictional force, which is opposite to the movement, because we're assuming that it's going up or that might go up, because remember, we're calculating the minimum force so it can start moving. So then after that, you know that you have to look at the frictional force on this side. It's going on the opposite direction on B, and then obviously you have the normal force that is coming from the other guy, which is right here. Sorry, the frictional force here is actually this one. All right, so let me just delete this. Once we have this, you just have to look at both free body diagrams and realize what you need to have in order to get the value. So if I look at this, it looks like maybe B will be the best way to go, because we have only two unknowns, which is normal right here and ND, and if we do that, then we can solve the equations and then carry those values into this particular one in order to find P. So going to B will make sense because we have the exact number of unknowns as we have of equations. So we have possible equations as sum of forces in the X, sum of forces in the Y. If we have two unknowns, we can solve the system. Whereas in this one, we have NC, we have normal, and we have P, and we only have two equations. So that's why we're going with B first. So sum of forces in the X direction, and don't forget the sign, will be equals to the normal force that multiplies sine of 15 because of this, and then plus 0.4 that is being multiplied by the normal, and also multiply by the cosine of 15, and this is minus ND, ND, and that's equals to 0, and I will call this my first equation. Then the sum of forces in the Y direction will be equals to the normal force that multiply cosine of 15 minus 0.4 that multiplies sine of 15 minus 0.3 that multiplies normal D minus 3000, which is the force that it's been applied to it, and this will be my equation number 2. So solving these equations, I will get that normal force is equals to 485 pounds, and then normal in D will be equals to 2894 pounds. With those two, now I can go into this wedge A and apply equations of equilibrium in order to find P. So like I said, take all those values that you calculated and then plug them into the free body diagram, as we can see here. And now we will focus on wedge A, and we will apply the same process, sum of forces in the x direction will be equals to P minus 0.3 that multiplies NC, and then we have minus 4,485 that is being multiplied by the sine of 15, and then we have minus 1794 cosine of 15, and this is equals to 0. That will be my first equation. And then sum of forces in the y direction, sorry I forgot the sign, will be equals to NC plus 0.4 that multiplies the normal, which is 4,485, and also sine of 15, the component of that normal force, minus 4,485 cosine of 15, and this is equal to 0. Solving these equations, we get that NC will be equals to 3,868 pounds, and finally P will be equals to 4,054 pounds, and my problem is solved. The important thing with this, okay, is that we can look at both of the free body diagrams and we can do the analysis so we don't waste time. Okay, if you went with A first, that will be a process that will take you nowhere, and it'll force you to go into B in order to find relationships that will make your system hotter. So my advice for you would be that spend as much time as possible doing the free body diagram. It has never been this important, okay? So you have to look at that and look at the forces that are involved and make a decision based on the data that you have in your hands. So we're gonna solve another problem. A force P is applied to move wedge A to the right. The spring is compressed a distance of 175 millimeters. The static friction coefficient is mu s equals to 0.35. For all contacting surfaces, neglect the weight of A and B, and then we need to calculate again the smallest force of P needed to move wedge A. So you have, as you see, the spring. Okay, remember that there is a force due to the spring, which is equals to, you should know that, but K times the displacement, or delta L. Okay, and then after that we also have the weight. Well, we don't have the weight, we have normal forces, we have P, we have the inclination equals to 10, and then what would be the plan? The plan would be to draw the free body diagram, and again I will just cross this one because I don't like when I've been told what to do, and I appreciate my students just going with their own analysis. Okay, so you will draw the free body diagram. The next step will be to look at both of them and then make the right decision so your calculations will not take forever. So the first thing that comes to my mind is that I need to calculate the force due to the spring, and so I can apply obviously the equations. So if I calculate the force of the spring, I know that is K, which is the constant of the spring, times the displacement, and I will get the value, which is 2.625 kilonewtons, and with that I can then apply the free body diagram on both of them, B and A. And you know, remember that when we have the equation, the graph, we're all working on this. You know, they're telling you that you need to calculate the minimum P so the object can start moving. When the object is about to move, it's right here, which is the frictional force will be at its max, and you know that at its max means that it's mu sub s times the normal. Okay, and I'm just trying to show you how it's the same theory that we talked at the beginning of the chapter, and that needs to be applied to all of the exercises when frictional force when frictional force has to be taken into consideration. Okay, so if the wedge is on the verge of moving to the right, then slipping will have to occur above contact surfaces, and therefore we can have these relationships, knowing that Fa it's equals to mu s and A, and I have the values of mu, which is 0.35, and then Na for Fb will be this. Okay, cool. So just by looking at these equations or these free body diagrams, I need to make a decision. So what do? I know that I need to calculate the normal in B, and the normal in A. So if I look at this one right here, I have normal B, normal A, and I have P. I wouldn't go with A. But when I look at this guy right here, I have NC, of course, and I have NB, and I have other things. But what is very important is that with a simple sum of forces in the y direction, you can find the value of NB, because you have this guy and only this guy in both. So therefore, right, if I do sum of forces in the y direction, I don't need to do anything else. I will realize that the sum of forces will be equals to normal in B minus 2.625 will be equals to 0. Normal B will be equals to 2.625 kilonewtons. So now all I have to do is just take this value into this equation. Now I have MB. The unknowns that I have will be P and NA. So it's very simple. This is only at B. Okay, with that, I will move then the known values into, normal force times mu s, and I will plug the values into the free body diagram, and all I have to do is sum of forces in the x direction and sum of forces in the y direction equals 0, and my problem should be solved because I have two equations and two unknowns. So I'll go first with the sum of forces in the y direction, because I just realized that I can just solve. I only have one unknown going into the y direction, which is NA. So if I do that, this will be equals to NA cosine of 10 minus 0.35, NA sine of 10 minus 2.625, and that is equals to 0. And A then will be 2.841 kilonewtons. Now I'll do the same. I will take this value into the following calculations. So sum of forces in the x direction will be equals to P, which is what I'm calculating, minus 0.35 that multiplies 2.625, which is the normal, minus 0.35, which is mu, and multiplies the normal that we just calculated, obviously its component, so cosine of 10, and then minus 2.841 sine of 10, and this is equals to 0. Solving the equation, I will know that P is equals to 2.39 kilonewtons. And that will solve the exercise. Guys, now that I've shown you with two examples how we can use friction, at the end of the day, the key with this chapter is looking at the free body diagram and making the right decision. Okay, which one do I go first? And when that happens, especially if you're at an exam, you have to take time and look at both of the free body diagrams so you can select the one that will make your life easier, and then move that value into the next one so you can find the unknowns that you're looking for. So this is a puzzle. You have all the pieces. All you have to do is to put them together, and with that you can solve any exercise. Guys, that's it for chapter number 8. We're very close to the end of the course. I hope that you enjoyed the video. Okay, let me know in the comments below. You can, tell me anything or shoot me an email in case you need more of one-on-one help, and I will be happy to provide you with that. But if you don't have any more questions, I will see you in the next video, which is chapter number 9. Thank you very much for watching.